In previous lecture, we talked about Drude model. Drude model is not a quantum mechanical theory, but just only the classical ballistic scattering mechanism. But now we will describe the theory of Sommerfeld theory. Yeah, Sommerfeld is very famous physicist. He was an advisor of the Heisenberg and Pauli, and Pauli and might be Heisenberg, Heisenberg and Pauli, and he was very great teacher, and he guided many famous physicists. And anyway, and Sommerfeld is one of the big guy in the region of the quantum mechanical period in the early 19th century, right? Yeah, anyway, then the Sommerfeld theory deals with the quantum mechanical description, and he deals with the metallic materials can be considered as a fermionic particles. And here, let's study for the basic theory of the metallic. Therefore, the basic theory of metallic materials is the Sommerfeld theory. Sommerfeld theory is a representative exact theory in metallic system. Here, the first one is the ground state. Ground state of the electron gas. Basically, Sommerfeld deals with the electron as gas, and later, by adopting this concept, Landau deals with interacting electrons as a liquid. Therefore, and later we call that as a Landau Fermi liquid theory. And anyway, Sommerfeld theory deals with the electron as electronic gas theory. And anyway, and let's consider for any electrons confined volume V. Then here we assume that many particles do not interact with each other, so that one electron is a representative particles, and also we only deal with a single particle problem. And the Schrödinger equation of the single electrons is that minus h bar square over 2m del square psi r equal to epsilon psi r, because we do not consider for potential energy, because it is a free electron. Free electron means that we do not consider for potential. It is a single electron. It is a Schrödinger equation of single particle free electron. Single particle free electron should satisfy the Schrödinger equations. Here because we assume that it is confined in a box with a length L. It is let's think that the cube, the n electrons do not interact with each other, and there is no potential. There is a freely moved, and also they are confined in a cube box. Therefore, in a cube box, we can apply the periodic boundary condition. Periodic boundary condition as that x, y, g plus L is equal to psi x, y, g equal to psi xy plus L g n equal to psi x plus L yg. It is a periodic boundary condition, and because the electron is a free electron, basically the wave function represent extended free particles. It is exponential I k dot r is the free particles. Here, the momentum operator can act as a wave function. Then h bar of I del psi kr. Then in other words, it is that partial r exponential I k dot r. Then because I cancel with each other, imaginary part cancel with each other, therefore it is h bar k exponential I k dot r. Therefore the momentum p can be write down h bar k in Fermi, in the Sommerfeld Fermi gas. And also the velocity means that here h bar k over m. From the boundary condition, it is typical quantum mechanical problems, and quantum mechanics says that because of the boundary condition, the potential, for example, psi k r in one-dimensional case, let's think about x, y, g and equal to psi k x plus L y g. It means that exponential I kxx, and anyway I do not consider for the yg component, and equal to exponential I kx x plus L. It means that exponential I kx L, likewise exponential I kyl and exponential I kyg should be 1. In other words, it is kxl should be 2 pi n. Therefore, and the kx is that 2 pi nx over L, and ky is that 2 pi ny over L, and kg is that 2 pi ng over L. And it is very important because the kx, this k value is momentum, because momentum is that it is momentum is h bar k, and therefore here the k value is quantized because nx, ny, and g are integer. Nx, ny, and g are integers. Therefore, the kx, ky, kg is the momentum. Momentum is quantized. And so energy is quantized because energy is that p square over e 2m, and it is identical h bar square k square over 2m. Therefore, energy also quantized. Here, in the real space, it is a real space expression, but in quantum mechanics or the solid state, we should consider for momentum space. In other words, it is k space. It is k space, kx, ky, kg space. It is momentum space. Then, because nx, ny, lg are integers, we can think that there are quantum states. Quantum states, for example, nx, ny, and g are all equal to 0. it is a 0 point, and also nx equal to 1, but ny and g equal to a 0 case, and also this point is that ny equal to 1, this one is that ng equal to 1. Then we can make that there is a quantized value, and in k-space, not all the energy level are occupied, but only specified quantized level should be considered. Therefore, I'm sorry. And like this, the quantized level like this, it is this point is ground state 0, 0, 0, and it is 1, 0, 0, and it is 0, 1, 0, and this point is the 0, 0, 1, and like this, and some points can be defined, and it can be make a very small cube. The length here, the length is that 2 pi of L, and also here 2 pi of L, and also here 2 pi of L, because it is 2 pi over L is the amplitude, the length of the momentum. Therefore, we can think that there is a small volume element in k space, and in this case, volume of k space, it is a unit volume, unit cell. Then it is that 2 pi over L cube, it is the small k space. Then we can occupy, when we can increase the n value, then somehow there is many particles can be occupied, and in large surface can be and for each quantum state can be occupied, and in general, because electrons are fermions, and the fermions do not occupy in a single level, and by considering the spin, one side, and spin up and spin down, 2 electrons can occupy in a single quantum level. Therefore, and because there are many electrons, like a huge number of electrons can occupy from the ground state to the more higher energy states, and also therefore the highest energy level, it is highest energy level, highest energy or the momentum, at ground state, it means that it is Fermi level. We call it as a Fermi level EF. Then, and anyway, this we say that it is a Fermi surface. Fermi surface is at 0 temperature. The electrons are all occupied in the quantum states, and the highest energy level is the Fermi surface. And therefore, the volume of the Fermi surface here, the energy epsilon f can be write down h bar square kf square over 2m. Here, it is a momentum space. Therefore, this momentum space and the highest energy level state is kf. we call it as Fermi momentum, and corresponding Fermi momentum, and we can think about the Fermi energy. And therefore, the volume of Fermi surface is that we call it is omega, capital omega. It is the 4/3 pi kf square is the volume of the Fermi surface. And when electrons make this spherical shell, spherical spherical ball, and it is the highest energy level is the Fermi momentum, and the corresponding energy is the highest energy is the Fermi energy at zero temperature. In this case, the ground state means that the zero temperature region. Here, then, in this case, the number of allowed states is the Fermi surface size divided by the unit cell volume. Unit cell volume is 2 pi over L cube. Then we can calculate the number of occupied states, and here it is 8 pi cube, and L cube is the V volume, omega V. Then here omega means that V over 8 pi cube, omega 4/3 pi kf cube. Then therefore it is that 6 pi square kf square V, and it is the number of allowed states. And here the V is that real volume, real sample volume, and kf is a Fermi momentum. Here the number of state per unit volume is that number of k states per unit volume is that V over 8 pi cube, and here it is volume of the k-space unit cell. Therefore, and because one single quantum state can occupy in one single quantum state, and the 2 electrons can occupy because of a spin up and down. Therefore, the number of electrons can occupy as 2 because of spin up and down, and it's a kf cube over 6 pi square V is the number of allowed states, and therefore it is kf cube over 3V square V. It is the number of allowed states, the number of electrons. At the Fermi surface. And here the carrier density is that n over V. It is kf cube over 3 pi square. It is carrier density. Here we say that kf is the Fermi wave vector, and it is that the highest level of occupied state. Here, therefore, Fermi momentum is that h bar kf, and as Fermi energy is that h bar square kf square over 2m. And Fermi energy is very important. I will describe the physical meaning of Fermi energy. And here then actually when we think about that the inverse 1 over n, then it means that V over n, this n carrier concentration, carrier density represented the momentum. Carrier density represented momentum, but in real space and the momentum space there is a reciprocal relationship. Therefore, a reciprocal n can be written down as in real space volume. Here, Rs means that radius of sphere. Because here in K space, this Fermi surface is a momentum space. This can be corresponding to the real space volume, real space, and the real space also may have the spherical volume, spherical sphere, and in real space, spherical sphere can be written down as Rs. The radius is Rs. Therefore, it is like it is a volume of the real space sphere, and therefore, then this can be written down as that in momentum space from this, then we can think that 3 pi square over kf cube. Therefore, then we can make a relationship between the momentum space and the real space, and kf is that 1 over Rs and 9 pi over 4 to the 1/3. Then it is that when you calculate 1.92 over Rs, because in ball radius can be defined by that h bar square over me square. It is that 0.529 times 10 to the minus 8 centimeter. We call it as a ball radius. Ball radius of the distance in real space distance in hydrogen molecule and hydrogen atom, and therefore, from the ball radius interpretation, it is that 3.63 over Rs over A0, and the unit is the 1 over Angstrom. Then Fermi momentum, it is a Fermi momentum value, and actually we do not know the real Rs over A0 value, but anyway we can estimate. Here the Vf is the Fermi velocity. Fermi velocity is over h bar kf over m. Therefore, it is when you calculate, it is 4.20 times 10 to the 8 over Rs over A0 centimeter per sec. And also Fermi energy is that h bar square kf square over 2m, and it is that E square, because from here in h bar square of m is corresponding to the A0 E square. Therefore, then it can be write down E square over 2A0 and Kf A0 square. Then in metallic elements, the Fermi energy is about 1.5 and 15 electron volt region. And experimentally, Fermi energy can be measured from the photoemission spectroscopy. Then when this Fermi energy divided by the Boltzmann constant, Boltzmann constant, then the electron volt, the energy can be make a temperature. Then it is about 20 to the 100 times 10 to the 3 Kelvin. It is very high temperature. Then also when you calculate the Fermi velocity is about h bar kf over m. Then it is about 0.01 c is the speed of light at zero temperature. Then it means that the energy is very high, and basically some students may think that at zero temperature is the absolute temperature, then all the materials freeze out, and basically the temperature is the entropy, and the kinetic energy itself gives rise to the temperature. And because the movement of electrons, it generates the entropy, and the entropy makes the heat, and it increases the temperature. Therefore, one may think that at zero temperature, all the electrons and atoms are freeze out, and there is a movement. All the electrons and atoms are freeze out, and stationary becomes a stationary state. But it is wrong, and in real system, because electrons are fermions. If the electrons are boson, it is we can think that all the particles can freeze out, but electrons are fermions, and it means that electrons occupy the quantum state from the lowest energy level to the highest energy level. And therefore, in highest energy level is the Fermi energy, and even at zero temperature, the Fermi energy level is very high, and the energy level is about 1.5 to the 15 electron volt, and the temperature corresponding to the several tens of Kelvin, or the 10,000 Kelvin. Yeah, and therefore it is very high temperature, and in our daily lives we live the 300 Kelvin. 300 Kelvin is very small temperature, and in the solid, and therefore even at zero temperature, the electron kinetic energy in metal and is very high, and the Fermi velocity is about 1% of the speed of light, and it is very high velocity. Therefore, then if the thermal excitation is negligible, and because the Fermi energy level is about 100,000 Kelvin, whether several thousand tens of thousand Kelvin, and it is very high temperature, and the room temperature 300 Kelvin is very negligible, and therefore the thermal excitation is not comparable to the Fermi energy. Therefore, even at room temperature in a metallic system, and even at room temperature, the Fermi energy is the dominant energy, and therefore the Fermi energy is very important in our daily lives also. and thermal excitation is negligible. And therefore, what from now on, we always think about the Fermi energy, because lowest energy level lowest energy level is not our interest, because low energy the high energy electrons overwhelm all the system, all the material system, and therefore I always stressed out that the Fermi energy is very important, and in the vicinity of Fermi energy, the band structure also very important near the Fermi energy, and the band structure near the Fermi energy contributes to the physical quantities like specific heat and electrical transport and something like that. Okay, then it is a zero temperature consideration, and in the next presentation I will describe for a finite temperature contribution.